Hi. Good afternoon. Welcome to numerical methods and modeling. We are trying to begin and finish on time. Not always possible, but we are trying. So, today we need to elevate a little bit our adrenaline levels because this is a bit difficult stuff I'm going to talk about, and it's a hard lecture for me because I have to try to explain things to you which are not easy. So they are not only not easy to explain, they are in themselves difficult, right? So there is inherent difficulty in this, and it would be helpful if your adrenaline and level of awakeness is high, so that you can stop or interfere to point to the stuff, to the things you are not getting, right? Because there will be surprises today, at least two, and one big one. Okay, so we are doing dynamics. So this is the plane. Okay, the aeroplane in the air, as you can see in the picture, translating and rotating, right? So if we want dynamics or relationship between forces and motion for an object in space, we need to deal with this. And we will start by looking again at this picture very quickly, okay, which simply shows the rigid body, which is composed of many small masses, MIs on radii Ri, right? So this is the nomenclature we are using today. So now, 3D dynamics, we look at translation, okay? And translation we have seen 50, 100 times in high school and at the university. And of course, we have the momentum being the sum of all these masses times velocities, which can be shown via relatively simple procedure to be mass of the body times velocity of the center of mass. Okay, and then if we want dynamics of it, the dynamics equation for translation is that the derivative of momentum is the sum of external forces, and mass is constant in classical physics, right? Not dependent on velocity. And this is mechanisms unit, so we are not considering rockets and other jet engines, which may produce systems with variable mass. So mass goes in front of differentiation operator, and we have derivative of the velocity of center of mass, which is the acceleration of the center of mass, which is piece of cake and creates an impression that this is a Newton's law, right? But it really is not. Newton's law is force equals mass times acceleration is for the point. And this looks very similar, but it is the application of the general principle to the translation of rigid body. So force is mass times acceleration of the center of mass. And now we have rotation. And looking back at this picture, we have masses at radii Ri. So we have our angular momentum is our momenta of all these small particles times pre-multiply vector product with R. So this is the definition, right? So let us now have a look how this thing actually looks like, this momentum, angular momentum. So we want, in a second, we want to use a dynamic law, right? We had a dynamic law for translation here, and here is the dynamic law for rotation. Derivative of the angular momentum equals to the sum of external torques or moments. Okay? So this H thing is this. Now, velocities okay, can be written down as angular velocity times radius, right? So if we look at this picture here, okay, so velocity of any point will be angular velocity of this thing multiplying the arm, right? So this we know from primary school. So if we look at this, we can, without any derivation of any equations, we can see that we have a vector of angular velocity multiplied by something, which I have here in blue, that depends on the distribution of mass, right? Masses and radii on which these masses are placed. So this thing is the distribution of mass, and this is the vector of angular velocity. And actually, the derivation will follow that this thing can be assembled into a matrix called inertia matrix, which is a 3×3 matrix. So we will have our angular momentum being equal to a 3×3 matrix of inertia that depends on the distribution of mass, okay, times the angular vector of angular velocity. Okay, so this is so far, I suppose, not particularly controversial. But the controversial or maybe a difficult thing pops up now. Because if we want to take the derivative of it, the green derivative, right, to use the dynamic law, so we want to take the derivative of this, right, this times this. And we would ultimately want this thing to behave the same as this, right? So we can take the derivative of this, and this keeps constant. But there are radii there, distances. So this thing is constant only in the coordinate system fixed on the body. Because in any other coordinate system, because the body is moving, these r's will be changing. Right? And if r's are changing, this is changing. And if this is changing, then if you wanted to take the derivative of this thing when I is changing, you are in deep mess. Imagine taking the derivative of variable moments of inertia and things like this. So we come to the unavoidable conclusion. Anyone who have been telling you in the past 18 years to use inertial coordinate systems to do dynamics was not telling you the truth. The truth is that for any system of interest complicated enough, one needs to do dynamics in this coordinate system fixed on the body. Because only in such a system, this I remains constant, and therefore we only need to deal with derivatives of this part. So I have this written down on another slide, which looks like this. We must use coordinate system fixed on the body. Or to maybe make this a little bit weaker, coordinate system in which inertia matrix remains constant. Okay, so we will see instances, very peculiar instances, when the system chosen is not fixed on the body, but still I is constant. Okay? So one now needs to unlearn the idea that one uses inertial coordinate systems. One has to suddenly accept that the normal way of doing dynamics is to use rotating coordinate systems or moving coordinate systems which move with the body. One now needs to recall that we luckily considered how to take derivatives in rotating systems while talking about kinematics, which means some of us at least, should know how to take these d over dt in the rotating system. And this is how the dynamics is done for anything beyond the simplest cases in year 11 at high school. So anything, cars, aeroplanes, helicopters, all of these things are done using coordinate systems, non-inertial coordinate systems, fixed on these moving things, because of the desire to keep inertial properties of the system constant in that coordinate system. Questions? Am I so persuasive, or is it too hard to even ask questions? I never know. Lecturers, generally speaking, have great trouble gauging whether the audience is lost because it's too hard or because it's lost because it's too easy. Two minutes to think about it?
Is it possible to differentiate the matrix inertia?
In principle, yes. But in the next 5 minutes, I will derive equations for the inertia matrix, and you will see how painful it would be to differentiate these equations. And therefore, it is never done.
Can you give a basic example of
Yes, the aeroplane. The aeroplane is doing something, right? All equations describing that aeroplane must be written down in the coordinate system fixed on the plane, and therefore non-inertial and moving with the plane, and not in the system fixed with the ground. Because in the system fixed with the ground, obviously these r's would be changing while the plane is moving, and then taking derivative of this would be beyond human capability. And actually anything that moves in a little bit more complicated manner. So car doing the turn, okay? Imagine dynamics of a vehicle going fast, taking a turn. So you have rotation because it's turning, but you have also rotation due to yielding of the suspension, okay? So you have three-dimensional rotation of the chassis. To sort it out, you must fix the coordinate system on the chassis and not on the road, okay? So now let us quickly look at how this matrix looks like, because of course you have seen this before, just in slightly different context. So how to compute inertia matrix, okay? This thing is in your handout, so it is directly taken from your handout, okay? L1, page L1. Okay? So this is the definition. The only thing here is that I have lowercase r, and I was using capital R. Okay? So this is the definition. So we put it in component form. Okay? X, Y, Z for the angular momentum, the distances, and the angular velocity. Okay? And then we have the identity from vector algebra, which you probably have seen, but I'm sure you forgot, which converts the two vector multiplications to scalar products. Okay, which means we will use this identity for these two guys. Okay, and we end up with something like this. So this is direct application of this identity to this guy. Okay, and then if we expand and write it down component by component, we end up with something like this. Okay, so we have some stuff depending on the mass distribution, right? Masses times coordinate square. So like, this is like square of distance, right? So it looks like mr square, right? And these guys have masses, and you have some coordinates multiplied with each other, which has the unit of meter square as well. Okay? And then components of angular velocity. Okay? And this actually can be collected, and is collected like this. Okay? So you have the inertia matrix that looks like this, and then definitions of entries are exactly given, given here, right? So these can be, of course, integrals for a continuous body or summation or things like this, right? So it's this. And now the nomenclature for this is that the diagonal components, these ixx, iyy, izz, are called moments of inertia. And off-diagonal components are called products of inertia. So now, probably, we can now see that taking time derivatives of all this stuff here, if x's and y's are changing in time, would be a nightmare. So we must put it in such a coordinate system that all of them are constant. Okay? So what have we seen in the past in primary school? Of course, we have seen the case when we had rotation around fixed axis z, okay, and the torque was omega times I, and this I was really izz, and this omega was really 0, 0 omega, right? So this is what we have seen in primary school, right? So rotation about fixed axis, right, with only z component of angular velocity, and then a symmetric body, only izz component from this whole matrix was entering into a simple scalar equation for, sorry, this should be d omega over dt, so angular acceleration. Say d omega z over dt, right? Angular acceleration times a moment of inertia gives torque. Okay? Oh, I even have it here. Right? For a symmetric body, we have diagonal matrix of inertia, and rotation around fixed axis just gives this equation for angular momentum, and consequently the torque will be derivative of this will be izz times d omega z dt. Okay? So we now can see the logic in this, hopefully. This, what I'm showing is a generalization of what you have seen for a simple rotation of a symmetric body around the fixed axis. Now, during the tutorials this week, the second tutorial probably, you will do some exercises to calculate inertia matrices for various things, like a snowman. and also our case study. Remember that we have this big rolling. For the case study, it is clear that to figure out the forces involved in producing this motion, we need to have the inertia matrix for that rolling. Now, luckily, we have also the handout, which gives us many instances for simple shapes, right? Sphere, hemisphere, cylinder, many, many things. So in practice, you rarely do integration, or mostly you look at your system and it is split into these shapes, and you just take the shape, the values from the tables. Or, for that matter, you have a CAD system, right? And if you do the drawing for your design in the CAD system, you can immediately extract inertial properties, right? Mass, center of gravity, and the inertia matrix, all these components. So the code would simply numerically conduct numerical integration for this, or actually explicitly use these for, say, some 1,000 or 5,000 masses, right? Would split your design into a few thousand small masses and then use this and then spit out the inertia matrix for anyone to see. Now, any questions about this? So, many things in engineering are symmetric. So let us have a quick look at how the symmetry affects the appearance of the mass matrix, inertia matrix. So let us look at this one. Okay? So this is symmetric about axis Y. So the stuff on the left-hand side and the stuff on the right-hand side of axis Y is the same. Okay? So you can see that if you look back at the equation, mxy times zy enters here, and you can see that if the system is symmetric, these things must be zero, because something will be computed on the right side and then on the left side with a negative sign, and it will go away. So often, just by looking at the thing, you can immediately see that then when you choose axis on the body conveniently, some of the products of inertia or all of the products of inertia will simply go away. Okay? So there will be zeros there. So there is even a picture here that shows many engineering structures that have many axes of symmetry, and by choosing these axes of symmetry in a smart way, and essentially understanding this picture and looking at the equations for products of inertia, you see which planes and axes of symmetry will result in which products of inertia disappearing. Okay? And so let us say often straightforward to choose axes so that we have symmetries that make products of inertia 0. Okay, so products of inertia are these off-diagonal entries, right? Well, the situation is even better because there is a theorem that says that for a body of completely arbitrary shape and distribution of mass, it is possible to find axes for which all products of inertia are equal to 0. Okay? And these axes are called principal axes. Okay? And obviously, they appear to be the coordinate system of choice to be used, right? Because for such a coordinate system, you have a diagonal inertia matrix, and things appear much easier then. Okay? So sometimes these principal axes can be found by inspection, by using the symmetries. But if not, then there is a mathematical procedure that allows us to find these axes, but I'm not covering this in the unit. Okay? So principal axes are always there. So everybody will have her or his principal axis. But where they are sometimes can be found by inspection, but sometimes one has to actually do the calculations. Now, another interesting observation, if we can have a look in our handout at the matrix of inertia for the sphere and the cube. Okay? So, of course, sphere is symmetrical, so all products of inertia go away, and this is the value for the actual number popping up on the diagonal. But if we look at the cube, which would be this one with all dimensions equal to a, you always also find that its products of inertia go away, and you have just a number popping up on the diagonal. So somehow, miraculously, from the point of view of inertial behavior, the cube cannot be distinguished from the sphere, right? So there is no clear-cut explanation why this is so. There is some feature of dynamics in 3D which makes the cube and the sphere identical from the point of view of inertial properties, even though they look pretty different. The sphere does not have sharp angles, does it? So the next observation is something very important, and we need to focus our minds on this for a second. So imagine the case almost as simple as in primary school. We are rotating our body around the fixed axis Z. Okay? But in the primary school, you rotated a symmetric body. Okay? Which means the body which has products of inertia equal to 0, so no off-diagonal components in the inertia matrix. But now we will be rotating the body which is not symmetric, okay, but still around the fixed axis. Okay? So this is what we are getting. This is the equation for our angular momentum. Inertia matrix times angular velocity, which is very simple because it's the fixed axis. And if we do the multiplication, we are getting this. So in primary school, you have seen only this, right? as I also made this note here, right? For a symmetric body, you only see this. Okay, and this is the torque, just IZZ times angular acceleration. But for a body of a general shape, you see this, and suddenly you realize that angular momentum is not parallel to angular velocity, which is the situation totally different to translational motion, when obviously momentum is parallel to velocity of the center of mass, but not for rotation. For rotation, as you can see, you have components which are non-zero in x and y directions, provided that you have non-zero products of inertia, right? So this is very scary. So I have even a picture for this, which is also very scary, right? Okay, for a general rigid body, you can have angular momentum in one direction and angular velocity in some other direction because of this. You see, when you look at the momentum, you have mass times velocity equals to momentum. Mass is a scalar. It does not affect the direction. But here you have a matrix 3 by 3, which may affect both the direction and the magnitude. And that's why you get this bizarre situation. So let us look, for example, at the rotor. Okay? So imagine a rotating machine rotating along axis Z with high angular velocity. So with fast speed, say 3,000 revs per minute for a turbine would be all right. So vector of angular velocity obviously is pointing along Z-axis, because this is how we understand the vector of angular velocity. Along the axis of rotation, direction as shown by the right-hand rule, and the magnitude, the spin, the speed of the spin. But if the vector of angular momentum is not parallel to the vector of angular velocity, it will be changing all the time, right? It will be, the tip of that vector will actually draw some kind of a circle. So the vector of angular momentum will be time dependent. We will be changing in time, okay? So when you have angular momentum changing in time, the basic principle of dynamics will tell you that there must be an external torque acting on the system, because we can't avoid this equation. If h0 is changing in time, the derivative is non-zero. If derivative is non-zero, we must have non-zero external torque. So now I am telling you this heresy. We have a rotation with constant angular velocity, and we still need external torque to maintain it, because we can't escape this purple equation. So the magnitude of the angular momentum is not changing, but because the direction is changing, derivative will be non-zero. We need external torque. Who is providing this external torque? The shaft. Which part of the shaft? Exactly. The bearings will have to generate reactions, of course, equal in value and opposite in directions, right? They must be equal in value and opposite in directions, because otherwise the net force would be non-zero and there would be acceleration of the center of mass and the thing would flow out, right? So equal value, opposite directions to generate the exact value of the external moment acting on the system to satisfy this equation. And because the thing is rotating at say 3,000 revs per minute, these forces in bearings would be changing direction 3,000 times a minute and will destroy our system pretty quick. So the principle of dynamic balancing is to make sure that it doesn't happen. Okay? So what is dynamic balancing? Dynamic balancing is making sure that H0 is along omega. If H0 is along omega, along z-axis, it will not change while this thing rotates, right? So this will be 0 and there will be no external moments. And we can see that this can happen only when we make sure that this guy and this guy are 0. So the dynamic balancing is making off-diagonal components in the inertial matrix 0, so that you end up just with this, right? And then H0 is along axis Z, and then everyone lives happily ever after, right? Any questions? Yes, please.
Does this H0 formula works for rotation about a fixed point, which is known?
Well, in this example, which is, where is the picture? Under the page. In this example, we have, this is a turbine rotating about fixed axis, Z, right? So IZZ will be the moment of inertia of this rotor around z-axis, but we must make sure that the products of inertia are 0, which means if it is perfectly symmetric, there is no problem, right? If it is not, how do wheel balance in your car is done? Well, the guy runs it on the machine, measures some reactions in bearings, and then adds weights in places to make these reactions 0, which means he's adding weights into this equation, right? Where is my equation slide? He adds weights into these equations here to make this sum go to 0. Right? Small masses here and there. I mean, of course, normally you don't, in the engineering system, you expect the unbalance to be small, right? Because it is supposed to be symmetric, but with your car, you hit, or my wife hit a curb, bent the wheel, so, so you need to do something, right? It's no longer balanced, so then when you go 85, it shakes your steering wheel, right? Because of these, exactly these forces in bearings, reactions in bearings, okay? So, of course, we need to think maybe one more time, a little bit carefully, about what these moments are. Okay, these moments here are real moments acting on the system, okay? Which means it's a couple of forces with which the supports are acting on the rotor. And of course, the third Newton law is telling us that therefore that rotor is acting on the support with forces of the same magnitude, opposite direction. And it is these forces which will destroy your machine. it will destroy the support. They will destroy the supports sooner or later, right? If they are big and variable, so this will fail in fatigue because it's many thousands of cycles per minute, right? Okay, so I will display this one as so that it gets recorded. Sometimes in the books, you find a term called radius of gyration. So it is actually the square root of the moment of inertia divided by the mass. Okay, so you can check that the unit of this, something like this, is just the unit of length. Okay. So what do you think? Does it make sense? Will it make sense at the exam? That's the question, right? These are deep conceptual issues, right? So solving 200 problems on this does not actually help much. It's more about having the clarity in your minds on the need, on what the inertia matrix is, and the consequent need of using systems fixed on the body, and then additional consequences of the mathematics of multiplying a 3x3 matrix with a 3x1 vector, right? That it can produce a vector that is in different direction, which means angular momentum does not need to be parallel to angular velocity. And, well, example with dynamic balancing is pretty straightforward, right? Okay, so I'll hang around for the next few minutes here. If you want to ask, you are welcome.